All right, just a quick test. All right, that looks good, I think. Seems all right to me. All right, cool. Hello and welcome to another, I don't know, episode stream on, oh, maybe I shouldn't show you emails. Hello, welcome to another episode of PureScript and Wasm. No, Wasm and PureScript. So, the last time around, I think we did build, finish the builder, I think. And then we actually went ahead and, hello Yappy, how's it going? Nice to have you on stream. So, last time around, we finished our builder, or like Wasm builder module implementation helper. And we used it to compile our very small and tiny expression language to WebAssembly, and we can run these. So let's just check that that still works. So I can say run. And what that is doing is it is generating WebAssembly code for this module, which is, if you can look over here, we're compiling our C, which was supposed to stand for complex expression 35 squared. 35 squared here computes 3 plus 4 times 5 or something. I mean, this is not even right. This isn't squared. This is doubled. Yeah, the name's terrible. Whatever. Anyway, this is a small little expression, arithmetic expression. We're compiling it to WebAssembly. We're executing it in nodes, binding to the WebAssembly engine of V8, and we get 70. And I think this is new since the last time around, so I went ahead and I did a bit of tedious work of giving all our data types a little show instance, so we can look at the generated code. It's kind of horrible. We can eventually do this properly if we feel like it by generating the text, the WebAssembly text format. For now, this is just for debugging purposes, and we're not going to need it much today because the plan is to not actually do any WebAssembly today. What I want to focus on today is to turn this little expert thingy into a language that is reasonable enough that we can play with it. So I want us to have a little bit of a language playground, I'd say. And I mean, this series is supposed to be focused on the backend part of a compiler, so code generation and the WebAssembly part. But while I'm fine with reading ASTs like this, I think it's probably, you're probably gonna, those of us that aren't writing ASTs for fun all day are gonna have a hard time to decipher what this means in terms of code, right? Because I mean, there's also the bit where we say, right, this is, what does this really mean? This means 35, the program down there, right? It's 35 equals, what do we say, 3 plus 4 times 5, so 3 plus 4 like so times 5, if I could type today, and then the result here is 35 times 2. I mean, yeah, if we're being honest, it's a lot easier to read this than to read this thing, right? So what we're going to do today is we're going to build ourselves a little bit of a language, which is also going to have a little more features than what we have right now, and write ourselves a parser for it. Again, the series is focused on the backend primarily, on the compiler backend, but so I won't be going into too much detail. We'll just build it, and we might get into more details on parsing and pretty printing when we, and if we ever deal with the text format for WebAssembly. So let's get started. So what I'm going to do is I'm going to create our own little AST module here that is going to hold the data types. Or let's just start with the parser right away. So we're going to define the data type inline, and then we can eventually pull that out, I'd say. So this is the parser, and we'll definitely need the prelude. And I haven't been parsing too much in PureScript, but I know that there's a parsing library, which is essentially I want to go from PureScript. So yep, you're asking the question. You want to go from PureScript to your AST? No. So what we're doing in this series is we're not trying to compile PureScript WebAssembly. We're compiling in PureScript. So we're using PureScript to write the compiler, but we're compiling our own little language because PureScript is way too complicated to make this an educational series, really. You could, of course, apply all the stuff we do in this series and apply it to PureScript, but you have to build so much more to be able to compile PureScript to WebAssembly. Okay. So I'm going to add a dependency on parsing because that's a parsing library we really use. And then I'll also just add a dependency in generics rep because I might want to have some show instances for the data types we'll define. And we can use that to get that. So I'm going to just make sure all of that was correct and we can build it. Right, yes. Okay. So this isn't a real project then. Well, what's a real project to you? It is real because it exists, it compiles code and it runs. But yeah, it's not meant to be a production. It's not meant to compile a language that is production ready or anything. It's it's an educational tool, really. Okay, so we're going to use the Pisco parsing library, and that library has a bit of a weird setup where if you look here, there's a billion modules, which you kind of need to put together. I'd prefer it if it was a lot more condensed, and you could just use one or two imports, but instead we'll have to use a couple of those. All right, yeah, sure. Have a good day. Okay, so parsing. We're going to use the language thing over here, and I think we're also going to use the token one. Okay. So we have a Java style, which is a thing which we can use to. So let me just finish this bit, and then we'll. Okay, so I should have. I was a little bit distracted. I should have started out by saying, let's look at a bit of how the code I actually want to write, what the code looks like. So let's just do a little bit of sketching here. So what we're going to have eventually, hopefully, is a language that looks a little something like this. So what I want to be able to do is I want to say, okay, this is the Fibonacci function, right? And the Fibonacci function says if x is less than 2. And let's just, to show off all the features I want this to have, write this out like so. So it's going to look a little Rust-ish in terms of the syntax we're using here, right? So if x is less than 2, this whole thing is going to return a 0 and, a 1. And otherwise it's going to return Fibonacci of x minus 1 plus Fibonacci of x minus 2. So a little bit of an imperative style language. And then what I'd like to be able to do is I'd like to write multiple functions followed by one another, and here in the main function here we're just going to compute the Fibonacci of 10. Okay, and so we have these like function declarations. We have still the little so this is still the arithmetics stuff we did before, right? So all of the features our previous expression language had are in here, right? We have these like infix operators for arithmetic expressions, but we also have an if statement, or like an if expression, and we have these like additional levels of structure here, where we have a level where we can define functions, a level where we can do let bindings and expressions, and then the expressions themselves. Okay. And so what I want to start out at, because it's the lowest level the syntax basically has, is the expressions. Okay. And so I'm going to leave this up there, I think, maybe, so we can reference it when we define our data types. So I'm going to say we have an expert, and it's a good practice if you ever find yourself defining an AST to have a parameter that you can use to fill in the binders and variables. You don't want to hard code those to strings ideally, so we're not doing that, even though there'll be strings for most of our compiler, I think, for now at least. Okay, so let's define the data type here, and what do we have? Well, we have int literals, right? These just carry around an int with them, and we'll also have bool literals. I haven't shown those yet, but of course those are just the true and false keywords, and we're gonna have those as well. Then what else do we have? We have binary operations. So this is something that a binary operator that combines two expressions. And expr a. So these are the two expressions, and this is the operator. Now we don't have a data type for operators yet, so let's define it. Let's define all the operations we'll have. So we'll have the ones we used to have. So add, sub, mul, and div. These are the arithmetics ones. But then if you check up here, this is actually a relational operator. So we'll have a bunch of relational operators as well. So we'll have less than, greater than, less than equals, greater than equals, and just equals. Okay, these are all the operators we'll have, and a binary operation takes one of these operators and uses it to combine two different expressions. Okay, so that's how we're going to read that. Then we have the if expression, right? And an if expression has exactly three expressions underneath it. So that's the first one is the condition, and the other two expressions are the branches, for now at least. And then do we have any more expressions here? Oh yes, we have a call, right? So this is a call, and a call is going to have an a, which is the name of the function it's calling, and then it's also going to have an array of arguments that it's passing onto that function. So the example we have here doesn't really make use of that. So we could say define the add function as well and say, well, just so we have that, and then this returns x plus y, and then we can use over here add the two recursive calls like so, and this shows that we have multiple arguments to functions. Okay, and in calls we have the same thing. So we're not doing the whole auto currying stuff for now because well, we're not going to have first class functions for now because that's a lot harder to compile, and we want to start simple and build our way up until we get a more complicated language. So do we have everything then? Binary operations, ifs, and calls. And I think that's going to be that for now. Yes, I think that's good. So this is the expression language we have. Now let's derive ourselves a quick generic instance here so we can show this thing. So we're going to derive that derive instance like so. And we need to import generic real quick. Okay, here we go. And then what we're going to do is we're going to say, okay, instance show expr. We show an expr of a. And well, for that to work out, we also need the a to be showable, right? And then we're going to say show x is equal to generic show of x. No. Why did my cursor move up there? Like so. And what do you not like? We don't have a show instance for op. That is correct. So let's define that really quick. Like so. And now that works. Okay, so now we have a little data types here. This is how our expression language is defined. So now let's get into the parsing bit. So we want to try and parse this. And again, I said I wasn't gonna talk about how this works too much. So I'm just gonna go ahead and we can talk about what that means in a bit. So I'm gonna define a gen token parser, which is kind of the lexer really. And I think it takes two parameters. So this is a string and I think identity. Like so. And then we're going to say L is equal to make token parser. And this is going to be our langdef, which we don't have yet. So let's define it. And our langdef is going to be based on Java, on the Java def. So we're going to say there's a Java def there, and that's ungen token parser or something, I think. Ungen language def Java style, like so. And then we're going to say that our langdef is, okay, so let's call it lang style. And our lang style is going to be our lang def wrapped up in the language def thing. So language def. This is the constructor of our lang def. And our lang def, and this is where the logic is finally going to happen. It's going to be Java style. And then we're going to update a couple fields in there. Like so. So if we look at Java style, how Java style is defined. Do you not want to go there for me? No, it doesn't work. Something's busted. Okay, so maybe we might actually need to look at Pursuit now to figure this out. So let's go and find the parsing module. And let's look into the, I think it's token. No, actually it's language. So here's where the stuff is defined. So this is the language def and gen language def. There we go. So these are the things. I think these most of these things are set decently well. So especially the identity and operator stuff is good. The things we'll need to override is we'll need to say these are the reserved names. So we have a couple of those. So language is going to have a function keyword. It's going to have the keyword for true and false, and it's going to have keywords for if and else. I think that's all the keywords we need for now. Let is also a keyword, so we'll put that in here as well. And then we'll also have reserved op names. I think is what it's called. Yes. So we're going to say, well, these are the operators we have. So plus, minus, times, slash, I think, right, for the division. I could type today slash less than, greater than, less than equals, greater than equals, like so, and we'll have equals, just double equals in terms of how we write it, like so. Okay, so what do you not like about this one? This is not Java style, this is Java def, right? Okay, so now this compiles. So here we go. So this is so this gives us a token parser, which is a thing we can, which is basically Alexa. So yeah, again, I wasn't going to go into too much detail. We can use this to parse like small bits of the language we have. Okay. And so I think we're now pretty much ready to say let's get started with our expression parser. So our expression parser, and here we're going to use the support this library brings for expression parsing. So it does have a thing which lets us build an operator table and then build an expression parser like this. So I'm just going to define ourselves a little parser type real quick, so because that makes it a little easier to define these things. So we'll have a parser, and I think there's a something like this. Let's just import that real quick. I think it's parser as p maybe. Let's just make sure that works. Sure. Okay, that works. So let's define expr. Expr then. So expr is going to be a parser for exprs of string. So variable names are in our source language of strings. So we're just going to output that for now. And now what we'll do is we'll use build expr parser to do this, but we need to fix this thing first. And this is because this is a recursive parser, and just was a strict language. So if we want to do parser combinators with recursive definitions, we need to use fix basically. So let's copy what we have over here and fix it to match what we needed to do. Okay, so it's not gonna like any of that. We just need to add a couple of imports first. So I'm not gonna use strings for these. What I'm gonna do is I'm gonna say this is a reserved op, because that's reserved. Those are reserved operators, right? And then these are different functions. So these are supposed to be the constructors for these, and we have one of these. So that's bin op. And then for this one, it's bin up of div. This one is bin up of mul, bin up of sub, and bin up of add. And now it's asking what is the stuff we want to, so this is an infix parser, right? So what's the thing that is around, that the infix operators are in between? And we're going to call that atom, and atom is a parser of expr string. So these are the smallest bits of expressions we have, and we are going to pass in as an argument to this the parser for full expressions, because again this is a recursive thing. So, and we're not going to define it for now. So hopefully this type checks. Well, we need to, as I said, we need to pass down the recursive reference. There we go. Okay, and so this is able to parse just the arithmetic expressions, but I like to group these things a little bit differently, so we're going to do that now. I like to have times and div have the exact same fixity, right? So these have the same fixity, so I'll move that up there. What do you not like about this? This is now going down there. So this is becoming a comma. We don't need this anymore. This goes down here. So does this compile? Yes, this compiles. Okay, so this is now grouping together the times division and multiplication. This is grouping together subtraction and addition. And then I'm going to do one more group, which is for all of the relational operators, which are going to bind the weakest, right? So we can have arithmetic expressions to the left and the right of comparisons. So this is a less than, this is a greater than. I'm going to just define all of them. So this is less than equals, greater than equals, and the last one is just equals. Okay. And what do you not like about this? I'm missing the closing parentheses over here, right? Okay, there we go. So this should now be able to parse infix expression for us, and we can actually test that. So what I'm going to do here is I'm going to say if I'm supposed to parse an atom, I'll just parse numbers for now. So we'll just say l.integer. Okay, and we're going to map our intlet constructor over that. Okay, so now this can just parse integers as atoms for now. Now we can check that this actually works. So what we're going to do is we're going to say, I'm going to comment all of this for now. And we're going to say console.log show. Now what we're going to do is we want to say parse expr, and we'll give it an input, and that input is what we'll define up here. So input is a string, like so. And that's going to be, so we should be able to say 3 plus 4 times 5, and it should group these things correctly for us. Okay. Now it's saying, well, parse expr is not a thing. That's right. We need to import it, and I need to define it first because we, as it turns out, haven't actually defined this yet. So parse expr is a function that takes a string and gives you either a parser or an expr of string. All right. So what we're going to do here is we're going to say run parser. Now we need to define the parser we're going to parse, and we'll start out by saying, okay, so step one is we eat all of the leading white space. Then we're going to parse an expression, yeah, and then we're going to expect this to have ended. So this is end of file, I think. I think this is actually imported from a different module. And now I think the input actually gets in here as the first argument. Okay, that works. And so we'll say up here, well, okay, I'm just going to export everything for now. We'll narrow down the export section when the time for that is right. And so if we spog run this thing now, we should be able to see a something. Well, okay, so yeah, I need to add an actual import for this. Okay, here we go. Let's go again. All right, here we go. And so this is parsed as an addition. So we're adding 3 to the multiplication of 4 and 5, which is exactly the right way to group this thing, right? And we can turn this around and say, okay, we're going to multiply these two together, and we're going to add 5. And if we run this, hopefully it groups 3 and 4, and then it adds 5 at the end. And it does exactly that, as you see, right? So this is the binary operation of addition, and the first argument is the multiplication, and the second argument is the literal 5. So the expression parser works. I'm gonna not bother with our language for now. Okay, so here we go. So the next thing is now that we need to parse all of these. Okay, so let's do that. So the way we write these parsers is we say, okay, we're going to try to parse one, and if that fails, we're going to parse a different one. And so let's try to parse the booleans, right? And so these are reserved keywords, right? True. And if we succeed in parsing true, we're going to return a boolet of true, right? And we need an import for this symbol. This is control.alt. And so, I mean, this is just a bunch of parser DSL. Parser DSLs are usually pretty infix heavy, so this is going to look a little cryptic, but it's also very nice and concise. Okay, so we have bool literals. I'm going to say, oh, we're missing something here. So one thing we don't have yet is vars. Right, so we're going to say we also have vars, and I'm going to put these right above the binary operation. Okay, so we can, this should be all we need to be able to parse all the literals we have. What else do we need? So the binary operators are handled by this thing. Okay, so what do we need? We need vars, ifs, and calls. Now, the thing about if is that it's easy to recognize because it starts right away with a reserved thing. So we're going to do that. And if we, and these, I mean, this is just how these DSLs work. So we're going to say, okay, so if I want to parse an if, I'm going to say the first thing I need to parse is a, well, I need to succeed in reading the reserved keyword if, right? And if that works, I will then parse an expression, right? This is the condition, okay? And that's the first argument to the if constructor. And then the second argument to the if constructor is the then branch. Now the then branch in our case is an expression surrounded in braces. So, and then the else branch is going to be the keyword else followed by a braced expression again, and this is the else expression. I think it's braces maybe. There we go. Okay. And so, yeah, the way to read this is the if constructor accepts 3 arguments. You can tell this up here. This thing parses the condition, this thing parses the then, and this parses the else. Okay, and so it's kind of cryptic, but at the same time it's really concise. So that's why it's worth it. I usually don't use infix operators much, but in parsing, well, parsing is really a DSL thing, so that's why I do that. So we should now be able to say if true 1, else 3. Right, let's see if that works. See, this is an if, and the condition is true, and then these are this is the then, this is the else branch. Okay, and we can make these a little more complicated. For example, I could make the then branch a binary of an expression. And then you can see right here that this is a binary expression now. Okay, so cool. So we can parse if expressions. And so the last thing we need for expressions is variables and calls. And now the thing is they both start with just an identifier. So we'll do that. We'll say, okay, we're starting out with an identifier. And then what do we have? So we have an ident here, right? And now we can try to parse a call of that ident. And the call is also going to accept the e. And if we fail to parse a call here, we're going to say, okay, then in that case, this is a var of ident. Okay, and so now it's complaining that it can't parse a call. That's correct. So this accepts the parser for expressions again. So we can figure out the recursion. Then it accepts the string, that is the function, the potential function name. And then this is an expression parser again. Okay. what is this? This is E. This is the name. And then what do we do? Okay, so I'm going to use ado here because it looks a little nicer. So what we're going to say, a call is, so we've already parsed the name, right? So the first thing we need to see is a parenthesized, something parenthesized. So, and we probably don't even need this. Let's just see. So we need a call, right? And a call is this first argument takes the function name it's calling, and then it parses a parenthesized list of expressions, and there is a comma separated list of expressions. So that's what this is. And the problem is here that a call, if we look up here, expects an array, and turns out that comma sep actually returns a list. So what we're going to do is we're just going to put an array from foldable in here, like so. And then this should parse, as far as I can tell. Why do you not like this? Oh, because this needs to be a map, right? What do you not like about this now? This needs to also be a map. So, okay. So what do you not like about this? Do I need to parenthesize this up? Probably. Okay, that's it. Okay, so this just needed some parentheses, and now I think we should be able to parse calls as well. So let's just make sure that works. So let's just put in our little call we actually want to make eventually. We can actually turn this whole thing into the expression we want to write eventually. So we say if x is less than 2, then we want to return 1. And else we're going to call Fibonacci of x minus 1 plus Fibonacci of x minus 2. Just like this, I think. So can we parse this? All right, so what do we have? We have an if, and the condition is whether x is less than 2, so that looks good. If it is, we're just going to return 1. Otherwise, we're going to have a binary operation that adds together a call to the Fibonacci function with a single argument that is x minus 1, and a call to the Fibonacci function with a single argument that is the subtraction of x and 2. So that looks exactly like the expression we wanted this to be. So that's our expression parser. Now, our language is a little more complicated than that, right? If we recall our little markdown thingy over here, we had actually something a little more complicated than that because we had this let binding up here. So we had some kind of declaration syntax, okay? So we're going to do that next. So we're going to say, this is expressions. That's all nice and good. But we're also going to have declarations. What are declarations? Well, we only have 2 right now. We have a let declaration, which binds an expression to a name. And the other case is an actual, just an expression, right? So just a naked expression, and that's just this. So declarations are reasonably simple, but they will become a little more complicated when we do more things with them. And okay, so we also want to show instance for that. So let's parse declarations then. So a declaration is a parser for a declaration of string. Okay. Declarations are pretty simple because the only thing we need to check if it's a let declaration, and we can tell that by it starting with a let. So if we were to parse a let declaration, what we need is as first is the name. So what we're going to start out is we're going to say, okay, so we need the reserved keyword that is let, okay, And then we need an identifier. So that's an identifier, and that's the binder that we're binding expression to. And then we need to see an equals, and for that we can use symbol. Okay, and then the second thing is just the thing after the equals. It's just an expression. Okay, and that works. And then if we fail to see all that, that means it must be an expression declaration, which is just expr d mapped over expr. Okay, so declars are really simple for now. Now, I don't want to go and try to parse this because I'm pretty confident it works. I don't want to spend more time on this. So let's define the thing that is the real fun, because that's the bit that if we check our language thing over here again, it's not just these blocks. The thing at the very top is function definitions, right? So we have top level function definitions, and a function has a name, has an argument list, and then it contains a list or an array of declarations. So let's do that. So let's say we have a func def. No, I'm not going to call it func definition. And so funcs are, as everything, parameterized by an a. So the func is just a single constructor here, really, because it has a name. That's the function name. Then it has an array of parameters, which are also just named. And then it contains an array of declarations, like so. So how do we parse these? So a func is a little bit more complicated in terms of how much is going on. That's why I'm using a do here. Okay, so a func is, starts out, we said the first thing we want to see is the reserved keyword fn, so reserved fn. Then we're going to see the name of the function. So this is l.identifier. So that's the name of the function. The next thing we're going to see is the parameter list, so params. And what is the parameter list? Well, the parameter list is a parenthesized, comma separated list of identifiers. And the whole thing is, again, this is going to return a list, but we need an array, so we're going to say array.fromFoldable here. So we've got the params, now the body, and the body is just a braced expression. Sorry, very similar to what we had before, but this time it's going to be semi-separated, right? Because we separate expression, so the declarations are separated by semicolons. And then at the end we say, okay, so that's a func then. A func has name, params, and body. Okay. And the last thing I'm going to say is that's the actual entry point. So so the top level thing is actually a bunch of funcs. So what we're going to do is we're going to say, okay, so this is maybe let's just write this as a parser. No, that's not. So parse funcs, which is the entry point we really want to use in the end, is either returns a parser or it returns an array of funcs. Okay, and so this has an input again. I'm going to run a parser on this input, and then the parser is going to be, well, again, we start by deleting all the leading white space, and then we're just going to parse many. Let's actually expect at least one. So we're going to parse some funcs, and then we expect again the input to have concluded. So we're going to say end of file, like so. And this needs to be func of string. There we go. And so this is the only function. Well, we might also parse expr for testing purposes, but this is really the main function we want to export. So we're going to say, okay, so let's parse a bunch of funcs. Okay, and so what we're going to do, and it's complaining that it can't show these, and that's because we haven't derived the show stuff for func yet. So let's just do that real quick. So now should no longer error. And if we try to run this right now, just for the fun of it, we should see an error where it says I was expecting a function keyword, but I'm not seeing anything. Okay, so, and that works. So what we should be able to say now is, okay, so this thing we have, right, that should be exactly the thing we're able to parse now. And I mean, that looks right. Do we want to go through it? I'm pretty confident it's right. So we now have a parser for this little language of ours, and a little AST. So let's break it up, put it in the right modules, and then we can see if we have any more time left, or if we're gonna work on actually compiling this at some point in the future. So I want to extract all the AST constructors because they shouldn't really live in the parser. So I'm going to move all of those out. So these go in the AST module. We're just going to export everything there is in here, because this stuff is really this is just data types that are going to be used in different places in our compiler. And so now this is going to start compiling, which is all right for me. So we're going to say I'm going to just add a bunch of imports for all of these. So this is the constructors for declarations, and we need to import the func data type as well as the constructor, but I think it's probably going to import the right thing for us. It does. Okay, so we don't no longer need the generic stuff in here because we're not deriving show instance anymore. Okay, so the parser is still here. I think we should still be able to run this thing. All right, cool. And so what we're going to do now is we're going to say, well, really the only entry points into this parser are parse funcs and parse expr. These are the two functions we're going to export, and that should still compile just fine. All right, cool. So that's how you build a little parser in PureScript. Again, I went pretty fast. I don't want this to be a tutorial on writing parsers, but I think it's really nice that we can do this in, I don't know, 77 lines, where 20 of them are imports. So I think that's just really neat. But this is supposed to be a series on compiling to WebAssembly, so let's not talk too much about languages that aren't WebAssembly. So this language of ours will now try to turn into WebAssembly, but I think this is a kind of a nice cutoff point. I've got some stuff to do today, so I'll end the stream here. There's going to be a nice little episode on how to parse a language, and then later today we'll get into the weeds of turning this into WebAssembly and executing it. So thank you very much for watching, and see you sometime later this day. Bye-bye.